process management is an integral part of any modern-day operating system. The OS must allocate resources to processes, enable processes to share and exchange information, protect the resources of each process from other processes and enable synchronization among processes. To meet these requirements, the OS must maintain a data structure for each process, which describes the state and resource ownership of that process, and which enables the OS to exert control over each process. Multiprogramming. In many modern operating systems, there can be more than one instance of a program loaded in memory at the same time. For example, more than one user could be executing the same program, each user having separate copies of the program loaded into memory. With some programs, it is possible to have one copy loaded into memory, while several users have shared access to it so that they each can execute the same program code. Such a program is said to be reentrant. The processor at any instant can only be executing one instruction from one program, but several processes can be sustained over a period of time by assigning each process to the processor at intervals while the remainder become temporarily inactive. A number of processes being executed over a period of time instead of at the same time is called concurrent execution. A multiprogramming or multitasking OS is a system executing many processes concurrently. Multiprogramming requires that the processor be allocated to each process for a period of time and allocated at an appropriate moment. If the processor is deallocated during the execution of a process, it must be done in such a way that it can be restarted later as easily as possible. There are two possible ways for an OS to regain control of the processor during a programmer unregistered trademark S execution. In order for the OS to perform deallocation or allocation, the process issues a system call. For example, an I/O request occurs requesting to access a file on hard disk. A hardware interrupt occurs. For example, a key was pressed on the keyboard, or a timer runs out. The stopping of one process and starting of another process is called a context switch or context change. In many modern operating systems, processes can consist of many sub-processes. This introduces the concept of a thread. A thread may be viewed as a sub-process. That is, a separate, independent sequence of execution within the code of one process. Threads are becoming increasingly important in the design of distributed and client-server systems and in software run on multiprocessor systems. How multiprogramming increases efficiency. A common trait observed among processes associated with most computer programs is that they alternate between CPU cycles and I/O cycles. For the portion of the time required for CPU cycles, the process is being executed. That is occupying the CPU. During the time required for I/O cycles, the process is not using the processor. Instead, it is either waiting to perform input-output, or is actually performing input-output. An example of this is the reading from or writing to a file on disk. Prior to the advent of multiprogramming, computers operated as single-user systems. Users of such systems quickly became aware that for much of the time that a computer was allocated to a single user, the processor was idle. When the user was entering information or debugging programs, for example, computer scientists observed that overall performance of the machine could be improved by letting a different process use the processor whenever one process was waiting for input-output. In a uniprogramming system, if n users were to execute programs with individual execution times of t1, t2, tn, then the total time, tune, to service the n processes of all n users would be, tune equals t1 plus t2 plus tn. However, because each process consumes both CPU cycles and I/O cycles, the time which each process actually uses the CPU is a very small fraction of the total execution time for the process. So, for process I, t a permel t, where t is the time process I spends using the CPU, and t is the total execution time for the process. That is the time for CPU cycles plus I/O cycles to be carried out until completion of the process. In fact, usually the sum of all the processor time, used by n processes, rarely exceeds a small fraction of the time to execute any one of the processes. Therefore, in uniprogramming systems, the processor lay idle for a considerable proportion of the time. To overcome this inefficiency, multiprogramming is now implemented in modern operating systems such as Linux, Unix and Microsoft Windows. This enables the processor to switch from one process, X, to another, Y, whenever X is involved in the I/O phase of its execution. Since the processing time is much less than a single job's runtime, the total time to service all end users with a multiprogramming system can be reduced to approximately T_multi equals max, T1, T2. Tn. Process creation. Operating systems need some ways to create processes. In a very simple system designed for running only a single application, it may be possible to have all the processes that will ever be needed be present when the system comes up. In general-purpose systems, however, some way is needed to create and terminate processes as needed during operation. There are 4 principal events that cause a process to be created: system initialization, execution of process creation, system call by a running process, a user request to create a new process, initiation of a batch job. When an operating system is booted, typically several processes are created. Some of these are foreground processes that interact with the user and perform work for them. Other are background processes, which are not associated with particular users, but instead have some specific function. For example, one background process may be designed to accept incoming emails, sleeping most of the day but suddenly springing to life when an incoming email arrives. Another background process may be designed to accept an incoming request for web pages hosted on the machine, waking up when a request arrives to service that request. Process creation in Unix and Linux are done through fork or clone system calls. There are several steps involved in process creation. The first step is the validation of whether the parent process has sufficient authorization to create a process. Upon successful validation, the parent process is copied almost entirely, with changes only to the unique process id, parent process, and user space. Each new process gets its own user space. Process termination. There are many reasons for process termination: batch job issues halt instruction, user logs off, process executes a service request to terminate, error and fault conditions, normal completion, time limit exceeded, memory unavailable, bounds violation. For example, attempted access of 11th element of a 10-element array, protection error. For example, attempted write to read-only file, arithmetic error. For example, attempted division by 0, time overrun. For example, process waited longer than a specified maximum for an event, I/O failure, invalid instruction. For example, when a process tries to execute data, privileged instruction, data misuse, operating system intervention. For example, to resolve a deadlock, parent terminates so child processes terminate, parent request, fatal error. Two-state process management model. The operating system unregistered trademark as principal responsibility is in controlling the execution of processes. This includes determining the interleaving pattern for execution and allocation of resources to processes. One part of designing an OS is to describe the behavior that we would like each process to exhibit. The simplest model is based on the fact that a process is either being executed by a processor or it is not. Thus, a process may be considered to be in one of two states, running or not running. When the operating system creates a new process, that process is initially labeled as not running, and is placed into a queue in the system in the not running state. The process then exists in main memory, and it waits in the queue for an opportunity to be executed. After some period of time, the currently running process will be interrupted, and moved from the running state to the not running state, making the processor available for a different process. The dispatch portion of the OS will then select, from the queue of not running processes, one of the waiting processes to transfer to the processor. The chosen process is then relabeled from a not running state to a running state, and its execution is either begun if it is a new process, or is resumed if it is a process which was interrupted at an earlier time. From this model we can identify some design elements of the OS, the need to represent, and keep track of each process. The state of a process. The queuing of NON running processes. Three-state process management model. Although the two-state process management model is a perfectly valid design for an operating system, the absence of a blocked state means that the processor lies idle when the active process changes from CPU cycles to I/O cycles. This design does not make efficient use of the processor. The three-state process management model is designed to overcome this problem, by introducing a new state called the blocked state. This state describes any process which is waiting for an I/O event to take place. In this case, an I/O event can mean the use of some device or a signal from another process. The three states in this model are, running the process that is currently being executed. Ready, a process that is queuing and prepared to execute when given the opportunity. Blocked, a process that cannot execute until some event occurs, such as the completion of an I/O operation. At any instant, a process is in one and only one of the three states. For a single processor computer, only one process can be in the running state at any one instant. There can be many processes in the ready and blocked states, and each of these states will have an associated queue for processes. Processes entering the system must go initially into the ready state. Processes can only enter the running state via the ready state. Processes normally leave the system from the running state. For each of the three states, the process occupies space in main memory. While the reason for most transitions from one state to another might be obvious, some may not be so clear. Running already, the most common reason for this transition is that the running process has reached a maximum allowable time for uninterrupted execution. That is, timeout occurs. Other reasons can be the imposition of priority levels as determined by the scheduling policy used for the low-level scheduler, and the arrival of a higher priority process into the ready state. Running a blocked A process is put into the blocked state if it requests something for which it must wait. A request to the OS is usually in the form of a system call. For example, requesting a file from disk or saving a section of code or data from memory to a file on disk. Five-state process management model. While the three-state model is sufficient to describe the behavior of processes with the given events, we have to extend the model to allow for other possible events, and for more sophisticated design. In particular, the use of a portion of the hard disk to emulate main memory requires additional states to describe the state of processes which are suspended from main memory, and placed in virtual memory. Of course, such processes can, at a future time, be resumed by being transferred back into main memory. The medium-level scheduler controls these events. A process can be suspended from the running, ready or blocked state, giving rise to two other states, namely, ready suspend and blocked suspend. A running process that is suspended becomes ready suspend, and a blocked process that is suspended becomes blocked suspend. A process can be suspended for a number of reasons, the most significant of which arises from the process being swapped out of memory by the memory management system in order to free memory for other processes. Other common reasons for a process being suspended are when one suspends execution while debugging a program, or when the system is monitoring processes. For the five-state process management model, consider the following transitions described in the next sections. Blocked, then suspend. Blocked, or if a process in the running state requires more memory, then at least one blocked process can be swapped out of memory onto disk. The transition can also be made for the blocked process if there are ready processes available, and the OS determines that the ready process it would like to dispatch requires more main memory to maintain adequate performance. Suspend blocked, then suspend ready. A process in the suspend blocked state is moved to the suspend ready state when the event for which it has been waiting occurs. Note that this requires the state information concerning suspended processes be accessible to the OS. Suspend ready, then ready. When there are no ready processes in main memory, the OS will need to bring one in to continue execution. In addition, it might be the case that a process in the ready suspend state has higher priority than any of the processes in the ready state. In that case, the OS designer may dictate that it is more important to get at the higher priority process than to minimize swapping. Suspended but ready. Normally, The OS would be designed so that the preference would be to suspend a blocked process rather than a ready one. Process description and control. Each process in the system is represented by a data structure called a process control block, or process descriptor in Linux, which performs the same function as a traveler's passport. The PCB contains the basic information about the job including, what it is, where it is going, how much of its processing has been completed, where it is stored, how much it has or spent in using resources, process identification. Each process is uniquely identified by the user or unregistered trademark S identification and a pointer connecting it to its descriptor. Process status. This indicates the current status of the process. Ready, running, blocked, ready suspend, blocked suspend, process state. This contains all of the information needed to indicate the current state of the job. Accounting. This contains information used mainly for billing purposes and for performance measurement. It indicates what kind of resources the process has used and for how long. Processor modes. Contemporary processors incorporate a mode bit to define the execution capability of a program in the processor. This bit can be set to kernel mode or user mode. Kernel mode is also commonly referred to as supervisor mode, monitor mode or ring 0. In kernel mode, the processor can execute every instruction in its hardware repertoire, whereas in user mode, it can only execute a subset of the instructions. Instructions that can be executed only in kernel mode are called kernel, privileged or protected instructions to distinguish them from the user mode instructions. For example, I/O instructions are privileged. So, if an application program executes in user mode, it cannot perform its own I/O. Instead, it must request the OS to perform I/O on its behalf. The system may logically extend the mode bit to define areas of memory to be used when the processor is in kernel mode versus user mode. If the mode bit is set to kernel mode, the process executing in the processor can access either the kernel or user partition of the memory. However, if user mode is set, the process can reference only the user memory space. We frequently refer to two classes of memory: user space and system space. In general, the mode bit extends the operating system's protection rights. The mode bit is set by the user mode trap instruction, also called a supervisor call instruction. This instruction sets the mode bit, and branches to a fixed location in the system space. Since only system code is loaded in the system space, only system code can be invoked via a trap. When the OS has completed the supervisor call, it resets the mode bit to user mode prior to the return. The kernel system concept. The parts of the OS critical to its correct operation execute in kernel mode, while other software and all application programs execute in user mode. This fundamental distinction is usually the irrefutable distinction between the operating system and other systems software. The part of the system executing in kernel supervisor state is called the kernel, or nucleus, of the operating system. The kernel operates as trusted software, meaning that when it was designed and implemented, it was intended to implement protection mechanisms that could not be covertly changed through the actions of untrusted software executing in user space. Extensions to the OS execute in user mode, so the OS does not rely on the correctness of those parts of the system software for correct operation of the OS. Hence, a fundamental design decision for any function to be incorporated into the OS is whether it needs to be implemented in the kernel. If it is implemented in the kernel, it will execute in kernel space, and have access to other parts of the kernel. It will also be trusted software by the other parts of the kernel. If the function is implemented to execute in user mode, it will have no access to kernel data structures. However, the advantage is that it will normally require very limited effort to invoke the function. While kernel-implemented functions may be easy to implement, the trap mechanism and authentication at the time of the call are usually relatively expensive. The kernel code runs fast, but there is a large performance overhead in the actual call. This is a subtle, but important point. Requesting system services. There are two techniques by which a program executing in user mode can request the kernel's services: system call, message passing, operating systems are designed with one or the other of these two facilities, but not both. First, assume that a user process wishes to invoke a particular target system function. For the system call approach, the user process uses the trap instruction. The idea is that the system call should appear to be an ordinary procedure call to the application program. The OS provides a library of user functions with names corresponding to each actual system call. Each of these stub functions contains a trap to the OS function. When the application program calls the stub, it executes the trap instruction, which switches the CPU to kernel mode, and then branches to the entry point of the function which is to be invoked. When the function completes, it switches the processor to user mode and then returns control to the user process, thus simulating a normal procedure return. In the message passing approach, the user process constructs a message that describes the desired service. Then it uses a trusted send function to pass the message to a trusted OS process. The send function serves the same purpose as the trap. That is, it carefully checks the message, switches the processor to kernel mode, and then delivers the message to a process that implements the target functions. Meanwhile, the user process waits for the result of the service request with a message receive operation. When the OS process completes the operation, it sends a message back to the user process. The distinction between two approaches has important consequences regarding the relative independence of the OS behavior from the application process behavior, and the resulting performance. As a rule of thumb, operating system based on a system call interface can be made more efficient than those requiring messages to be exchanged between distinct processes. This is the case, even though the system call must be implemented with a trap instruction. That is, even though the trap is relatively expensive to perform, it is more efficient than the message passing approach, where there are generally higher costs associated with process multiplexing, message formation and message copying. The system call approach has the interesting property that there is not necessarily any OS process. Instead, a process executing in user mode changes to kernel mode when it is executing kernel code, and switches back to user mode when it returns from the OS call. If, on the other hand, the OS is designed as a set of separate processes, it is usually easier to design it so that it gets control of the machine in special situations, than if the kernel is simply a collection of functions executed by users' processes in kernel mode. Even procedure-based operating systems usually find it necessary to include at least a few system processes to handle situations whereby the machine is otherwise idle, such as scheduling and handling the network. See also, process isolation. Sources: Operating System Incorporating Windows and Unix, Colin Ritchie. ISBN 0-8264-6416-5, Operating Systems, William Stallings, Prentice Hall, Multiprogramming, Process Description and Control, Operating Systems A Modern Perspective, Gary Nutt, Addison Wesley. Process Management Models, Scheduling, Unix System v Release 4, Modern Operating Systems, Andrew Tannenbaum, Prentice Hall. Operating System Concepts, Syllabus Charts, Galvin and Gunn, John Wiley & Sons. References, http sunivesblogspot.com 09/sneak peek into Linux kernel chapter 2 HTML. External links